So guys, we are no, wait, hold on. Option. Yeah. Okay, now we're ready to go. So guys, today what we're going to do, and you guys understand this, right? We're not wrapping up the unit today. We're going to wrap up the unit on Friday by talking about Le Chatelier's principle. It's short, it's concise. Same side does the opposite, opposite side does the same. We're going to apply that to gas phase processes and talk about pressure and equilibria, but that's the only new stuff on Friday. Guys, today, I wish that there was some way that I could rub my crystal ball and have you look into the future. Guys, because today you are going to learn a mathematical process for studying equilibria that will serve you throughout this year. I'll be honest with you, I did not learn this process as an undergraduate when I got my chem degree. I learned this completely differently. This is better. These are not my ideas. I lifted them right out of the textbook. Other AP Chem books teach this differently. This is best. So if you get into a university setting and your university professors don't teach you this, you get the opportunity to be a hero because you can teach this to your classmates, which could lead to dating opportunities. So guys, this is good stuff. And right, see? And guys, this stuff we're going to be doing literally for the rest of the year. So what is it? Well, guys, what we're going to do today is we're going to talk about how to mathematically dissect equilibria. So guys, don't let equilibria just be a word. Think about everything that you now know about equilibria. And for some of you, your head goes to the flippy tubes, right? For some of you, like Brandon, it seems like you prefer to think about this mathematically, and you've got the K ratios and the concentration ratios and big K. Guys, wherever your head goes, let's talk about equilibria. So, what do we know about equilibria? What is equal at equilibria? The forward and reverse rates. What about concentrations? Are they equal? What are they? Constant. And what determines that product divided by reactant ratio at equilibrium? The values of little k, right? And we talked about that. And guys, don't belabor that. That's not, you won't see many, like maybe a multiple choice question or two on the AP test. Not a big deal. But you need to understand that those k values, the ratio of products to reactants is dependent on little k values. So guys, now that we sort of have a general sense about what equilibria is all about, we understood how to write these k expressions, right? And we said that K is divided by the concentration of products divided by the concentration of reactants. And then guys, we've got these exponents that show up in these expressions. Where do they come from? Where do the exponents come from? The coefficients from the balanced equation in a way that we cannot make the coefficients the exponents when we're doing rate laws. And we don't want to dig into that again, but we understand that the exponents are the coefficients. And then guys, the last thing we need to touch on was this idea. I think this was the example that we looked at. So we've got soluble silver nitrate, soluble sodium chloride. We get insoluble silver chloride and soluble sodium nitrate. If we write the Kc expression for that, one of these doesn't get included in the expression. Which one? Why the solid, which in this case is the silver chloride. And remember, we talked about the idea that solids and what other substance does never show up in the equilibrium expressions? Liquids. So solids and liquids never show up in the Kc expressions. Again, and AP professors would die to hear you say this. But guys, for us, the reasoning is because they don't have pressures and they don't have concentrations, because solids and liquids don't have pressures because they're not gases, and they don't dissolve in water, and therefore they don't get included in the Kc values. Are we all okay with all of that? Go ahead. Yeah, so if you want to look at the other side of it, okay, if gases and liquids don't make the cut, what does? And so the answer is in Kc values, as the name suggests, it's things that dissolve in water, soluble substances. Kp's would be gases with pressures. Is that okay? And then you're going to find in chapter 16 and 17, we're going to talk about a whole lot of specific things that do dissolve in water, like acids and bases and even water. We're going to talk about water dissolving in water. It's a little crazy. So we're actually going to figure out the molarity of water in water. I know. Okay. It's 10 to the negative 14th molar. We'll talk later. So, guys, are we all on the same level ground? We okay? Okay. So, guys, what we're going to do now is we are going to learn to solve Kc expressions. And you're going, wait a minute, kind of learned how to do this last year. Well, yeah, but it gets better. So, guys, this then is the idea. And I know you can't help yourselves, right? You got to write it down. Go ahead. Go ahead. You guys are pathetic. It's really true. But what do you do when I tell you not to write it down? You still write it down. So, guys, then maybe we should actually, you know what, after we are done with the AP test, remind me, have I ever talked with you about the really interesting research they did at I think it was Stanford, about note-taking and retention, learning?
Yeah, they said when teachers say don't take notes, it's going to be on the test.
No, that's not education research. That's teachers being manipulative. Go ahead. Yeah, and I don't want to talk about it, but that's exactly, so maybe I must have shared that last year with some general chem class. Remind me after we're done with the AP test, and I'll actually print the research and show it to you. Guys, it turns out that note-taking, especially at the college level, decreases comprehension. We'll talk later. Okay, so guys, with that said, here's what we're going to tackle today. When we solve these, and notice the word calculation. When we do these equilibrium calculations, guys, there are two primary types of calculations you're going to make. So let's be clear. When we do a Kc value, we've got product X, product Y, reactant W, reactant Z, right? So guys, what goes in the boxes? Molarities. When? Molarities at what conditions? Good. Remember, and then we talked about Q, which was solving Kc at non-equilibrium conditions. But guys, fundamentally, we've got to be comfortable with the idea that the values that go in the boxes are at equilibrium. So, with that said, these are then the two types of calculations we're going to make. First of all, we're going to do calculations where we know the equilibrium concentrations, the equilibrium conditions. I use the generic term conditions because these could be pressures. This is kind of the stuff you learned to do last year. This is where this gets weird. Guys, we are going to solve equilibrium calculations when we don't know the conditions at equilibrium. And this is not Q. This is not fine. We'll just use conditions we'll just use concentrations at other conditions. This is, they're not going to tell us the concentrations at equilibrium, and we're still going to solve Kc expressions as if we knew the concentrations at equilibrium. And guys, the logic behind this is beautiful. And you're going to learn a mathematical construct called ice boxes. ICE is obviously an acronym, but you'll learn to solve these using what are called ice boxes. So you ready to go? Guys, all we're going to do for the rest of the day is problem solve. You're good? Okay, so this one you should be able to solve. For the Haber process, the Kp value is this at 500 Celsius. And guys, in these problems, they will always give you the temperature. It doesn't matter. The only reason they give you the temperature is because it makes that true. Guys, think about this. What is Kp a representation of? Products divided by reactants. For our stupid tube thing, it was 7/3. What determines 7/3? The value for the small k's, right? Can those small k's change? Yeah, temperature, concentration, catalyst. So they give you the temperature simply because that's what makes this true. Ignore it. So the Haber process Ksp is this. In an equilibrium mixture of the three gases, again at 500, the partial pressures are bump and bump. What is the partial pressure of NH3? You've got 2.5 minutes. Go get them. If you're thinking to yourself, wait, what's the Haber process? Remember, that's the one you need to memorize, right? All right, let me prime the pump. Diatomic nitrogen reacting with diatomic hydrogen to produce ammonia, which is NH3. You balance it. Again, diatomic hydrogen, diatomic nitrogen, and NH3, which is ammonia, not ammonium. Ammonium is NH4, the ion. Oh, yeah. This is the awkward pause in the screencast where people think their computers have crashed. What we need is elevator music. What? I know, that's a good point. Have you guys seen the movie The Blues Brothers? There's a wonderful elevator music scene. Neither. They just shut down my website. Are you done? Almost. Are you helping him with his calculator? Is he struggling? Oh. Hey, Kami, help me make my calculator work. So guys, allow me to write down the balanced equation. Oops. So guys, are we far enough into this that it would be appropriate for me to start solving it? Is that okay? Oh, this isn't one where we're solving for Kc. Guys, what I find is this. Are you at the point where I can share a thought with you? So fundamentally, what you're going to find is that when you're solving these problems, you're either going to be solving for Kc or you're going to be solving for one of the concentrations, right? Guys, frankly, I like to use different problem-solving structures. See if this makes sense. I like to use different problem-solving structures depending on what I'm solving for. If I'm solving for Kc, I like to start on the far left and just work to the right, because it would be Kc is equal to products divided by reactants, plug in the numbers, come up with the value. It just makes sense to go left to right. Guys, to me, when I'm solving for a concentration, I like to work down. because it isn't something that is just continually equal to itself. So in this case, because I know I'm solving for a concentration, I'm going to work down. So the first question is, what does it mean to show your work, right? Because you know that the AP graders require you to show your work. And so the first thing that always entails is writing down an equation. So do you need to write down Kc is equal to products divided by reactants? You do not. Guys, you simply build your Kc expression. So Kc is equal to NH3. Oh, this is pressures, isn't it? Thank you. Sorry. Kp, I mean, it's the same idea. You just represent this a little differently. So this is equal to the partial pressure of NH3, the quantity squared, and the partial pressure of N2 times the partial pressure of H2, and that would be cubed. Am I okay? Okay. Then, guys, plugging in values, this would be 1.45 times 10 to the negative fifth, and that would be equal to x squared divided by 0.432 atmospheres times 0.928 atmospheres cubed. And guys, frankly, my preference would be to not have to do the math. What's the answer? What I meant to say was, how about if I do the math? So I've got 0.928, and that is cubed. And then I'm going to multiply that by 0.432, and I'm going to multiply that by 1.45 times 10 to the negative fifth, and I get 4.9 times 10 to the negative sixth. Oh, square root, thank you. So 2.2 times 10 to the negative third. Okay. Did you get this? That's when you want to stop. Okay. But guys, understand that's technically not right, right? Units. Yeah, this is atmospheres. Be careful. When you're solving for Kc, and I don't know if we directly talked about this. Guys, Kc is a dimension, or I'm sorry, Kp. Kp is a dimensionless number because it's a ratio. But we're not solving for Kp or Kc. We're not solving for K. We're solving for, in this case, a pressure. So that number requires units. You okay? Okay. So guys, this is a question that I would have felt totally comfortable throwing your way last year, other than that it was a pressure rather than a concentration equilibria. But the math behind this is algebraic. The other thing that you might see is they would give you all of the pressures, and then you solve for K. We okay? Yeah. Yeah, so we know this is right. I'd be happy to sit down and help you fiddle with your calculator later. You guys okay? Okay, so guys, now things are going to change. We are now going to solve K expressions when we do not know the equilibrium conditions. Here's how. You may want to write this down. Here's how to solve these problems. Are any of you right now a little short of breath? Remember how in general chemistry everything had steps? How do you solve this problem? Step 1, convert to moles. Step 2, divide by the smallest number of moles. Step 3, write the empirical formula. Step 1, start with the mass. Step 2, convert to moles. Step 3, apply the stoichiometric ratio. Step 4, convert. Remember how everything in general chemistry had steps? Have you ever thought about how technically mindless general chemistry is? Yeah, and forgive me if this sounds condescending, but I really think that if I had an intuitive enough monkey, I could probably get that monkey through general chem. Because if you can follow rules, you can pass general chemistry. It's sad, but and I think you guys struggled with this last year, right? Where it really was, teach you a concept, teach you how to solve the problems by following the steps. Your homework was so stinking repetitious because it was 11 of the same exact problem with different numbers. And then when you took the test, you just did the 12th problem that was exactly like the first 11, just with different numbers, right? That's what makes AP chemistry hard in a lot of ways, right? Because it's all synthetic. There's no steps. It's, oh my gosh, learn some ideas, apply them here, and then let's apply them in some other places, and then apply them in some other places. Well, guess what? This has got steps. I know. Here they come. Step 1, write a balanced equation. Whose lunch is that? Maybe. My concern is I don't want to violate somebody that's not a part of our group. We have group norms that allow us to violate each other's lunches. I fear that somebody that's not a part of the tribe wouldn't get it.
You should stick the sandwich to the board, just like stick a thumbtack just through it.
So Mr. Maurer, several years ago, left his wallet at lunch, and I'm such an idiot. I shot pictures of it and put it up on KSL. Yeah, it seemed like the thing to do. Not thinking that one of the pictures had his credit card number on it. It occurred to me in about 30 seconds and I took it back down, but yeah, thankfully there were no views. Okay, so guys, step number 2, create an ice box. And guys, again, ICE is an acronym. And we'll talk about that in a minute. Now guys, I would suggest to you that you don't need to write down the next 2 subpoints. Please don't. But what this ICE box allows you to do is to create a matrix, if you will, that allows you to do some logical predicting. When you do, and again, don't write this down. When you do, what you're going to do is you're going to use a variable x to represent changes in concentration. Not the concentrations, but changes in concentration as a reaction goes from initial conditions to equilibrium. When you do that, you then use these variables as placeholders in your equilibrium expression, your Kc expression. I know that doesn't make sense, but it will. Then what you will do, and this you do want to write down, you will then plug these values into the expression, or these expressions into the Kc expression. That's a lot of expressions. And you'll solve for x. Then what you'll do is you'll come back and you will then calculate the equilibrium concentrations by using that x value back in the icebox. And you're going, what are you talking about? I'll show you. So guys, we're going to solve 2 problems. And then we'll go to lab. You okay? No, just, you don't have to write anything down. You'll probably learn more if you don't, but you guys are codependent. But these 2, don't write down. So guys, we're going to solve 2 of these as soon as you give me permission to move on. Good? Good? Okay. So guys, it goes like this. I would suggest you don't write these down. I'll tell you why in a minute. Okay, I'll tell you now. They're in your book. Don't look, but these are, I lifted them right out of the sample problems in your book. So it says this. It says a mixture of this number of moles of H2 and this number of moles of I2 is placed in a 5-liter container. Again, there's the temperature. We don't care. And it's allowed to come to equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is this. Calculate Kc. Okay, so guys, what we're going to do to solve this is first of all acknowledge that we're given some data, right? They tell us a mixture of this many moles of H2 and this many moles of I2. And you put those in a 5-liter vessel. Can you picture a 2-liter bottle? And then another one, and then half of another one, 5 liters? Okay, so you take that vessel and you put this many moles of H2 and I2 in there, and you allow them to react and come to equilibrium. Then you analyze the equilibrium mixture and you find the molarity of the HI. And again, this is a gas phase reaction, so we're assuming that molarity is moles of gas divided by liters of container. Okay. The question is, what's Kc? Well, guys, let's get started on this. So the first thing that we need to do is we need to write a balanced equation. Here's the trick. Make it big. And let me show you what big looks like. So guys, when you write your balanced equation, we're going to go H2, and then relative to the scale, like this is going to be the whole size of a line, and then you're going to skip maybe 1.5 centimeters, 3/4 of an inch, plus. Then skip another 3/4 of an inch, I2, then another 3/4 of an inch, equilibrium sign, and then your product, again skipping 3/4 of an inch, HI. You okay? You okay? Okay. Now guys, what you're going to do next is you're going to skip down 5 lines. I don't have the luxury of doing that because I'm going to be writing below the surface of my board or of my desk. So I'm going to grab a clean page. The next thing we're going to do after we balance this equation is we're going to write our Kc expression. But we need to balance this first. Is it really that easy? That was silly. Okay. And guys, we're going to write our Kc expression. I'm going to do this. If I write down here, is that okay? Is that in bounds? I'd like to do that because, guys, we're solving for Kc, right? And so my problem-solving strategy tends to flow left to right. So I think I can move down low enough, and if I just write horizontally, I think we'll be okay. You're going to skip down 5 lines, okay? And I'm just going to go down here. So let's write our Kc expression. So Kc is equal to, again, we don't need to write products divided by reactants. We need to know our products and reactants. So we've got HI, that's squared, right? And then H2 and I2. Am I okay? Okay. Now, guys, this is where you have an advantage over me because you have a full sheet of paper. Let's talk. So guys, now we need to think about, because we understand our end game here, right? The end game for this is we want to solve for Kc. So we need values to plug in for Kc. And we've got problems all over the place. So guys, let's talk about why we have problems. So first of all, this number right here. Can we, and I'm explaining, just follow. So guys, can we plug this number in right here for H2? No, there's 2 reasons why not. Can you see either one of them? First of all, it's not a molarity. Remember, this is a concentration equilibrium, and this is not a concentration. This is a number of moles. So we've got to make that a concentration. How will we do that? we'll divide by 5 liters, right? We've got those weird concentration units, which is moles divided by liter of the container. So we'll divide by 5. So now we've got a molarity. Can we plug that in for H2? Why not? It's initial. Good, Catherine. It's not at equilibrium. And remember how we talked. That's why I accented this earlier. Guys, these are equilibrium values. And it very clearly and specifically tells you, where does it say it? And does it say initial? Placed in 5 liters allowed. Okay, so it comes to equilibrium. So this is where you're starting. That is not an equilibrium condition. So it can't go in the equilibrium expression because it's not at equilibrium. So what are we going to do to fix this? Well, guys, we're going to convert these to molarities. Let's do that first. And guys, I'm going to have to do this on another screen. You could do that. These are what are called side calculations. If you've got room over here, you know what? I'm going to make room over here. So let's do these side calculations. So, and I'm going to write small. So molarity is moles divided by liters. Moles, and I'm going to be horrible with significant digits. 10 to the negative third divided by 5. So that's 1 times 10 to the negative third. And guys, would you just give me permission to get rid of significant digits altogether right now? Is that okay? Frankly, it'll just simplify the rest of it. Understand, don't do this. This isn't okay, but I'm going to do it anyway. So there's 1. And then doing our second one, molarity is moles divided by liters is 1 times 10 to the negative second divided by 5. Is that 0.002? 002? So 2 times 10 to the negative third. Is that right? Why does that feel wrong? Okay. And that's molar as well. Was that okay? We need molarities. But now we've got molarities. But as Catherine said, we still can't plug them into KC because they're initial conditions and not final conditions. So what do we do now? Guys, this is where we build our ice box. Are we good on those calculations over there? Is that okay? You guys keep them. I'm going to get rid of this because it's just going to be clutter for now. So I'm just going to get rid of this and you guys can feed me the numbers. Okay, so now guys, we need to address the other problem. And the other problem is, while we do know the molarities, we can't put them in here because they're not at equilibrium. Although, did you notice this one is? That one is at equilibrium, and it's a molarity, so that one's good. So what are we going to do to get the other equilibrium molarities? Here's what we do. I'm going to ignore you. What we do, guys, do this with me. We icebox this. What you're going to do is underneath the balanced equation, you are going to write the acronym ICE. And I'm going to give myself a yes, no, yes, no. So what does it stand for? The I is initial. The C is not concentration. The C is change. What's the E? Equilibrium. So guys, and please don't write this down, but functionally what we have just created, and again, don't write this down, what we've just created is a matrix. Can you picture that we have now created a 9-cell matrix? We have places to write initial concentrations. We have places to write changes. We have places to write equilibrium conditions. But guys, we don't write the grid, but we understand that it's there. And now what we can do is we can go back to the problem and gather together all the information that we're given and put it in the matrix. So, guys, this number, 5 whatever moles of H2, we converted it to a molarity. Where does that molarity then fit in the matrix? Where? So it's of H2, but is it initial, change, or equilibrium? Initial. So this is, what was it, 1? 1 times 10 to the negative third molar. don't like the way that's lining up. I'm not doing anything different. Oh gosh. I just want to give myself a little more space because I think you're going to find, so I, C, E, 1 times 10 to the negative what? Third molar. That's better. We got that from this calculation over here that I erased. Remember we took...
But we took the 5 times 10 to the negative 3 divided by 5 meters.
Uh-huh.
That worked out to be 10 1 times. Yeah.
Okay. Now, guys, we need the value for iodine. We were given an amount. We converted it to a concentration. Was it 2 times 10 to the negative third? Where does that fit? 2 times 10 to the negative 2 or 3? 3, right? 3? I think it's 3. If I wrote 2, I was wrong. Yeah. We okay? So, guys, where does it go in the matrix? Yeah, right here. So 2 times 10 to the negative third molar. We're not done. Because we're given another bit of information. We are given this, which is about HI, and it's a molarity. But read on, guys, and it says, analysis of the equilibrium mixture is this value. Where does it fit in the grid? Is it initial, change, or equilibrium? Equilibrium for which substance? Product. So that brings us down to this quadrant, and this is 1.87 times 10 to the negative third molar. Hold on. Let's make sure we're all there before we move forward. So guys, other than questions about, well, and maybe even questions about where did these two molarities come from, but allow me to answer the question. We did the side calculations that was molarity was moles divided by liters. There's your moles, there's your liters. Do the math similarly with the other. So guys, are we okay to hear? Okay. I would propose to you, however, because look at what we've done. We've taken all the numbers from the problem and put it in our icebox. There's one other value that we've neglected. There's one other cell in the grid that we can fill in. Which one? Brandon, you're about to wet your pants. Go ahead. Which one?
That's going to be initially 0.
Right. That's initially 0. Guys, by definition, before a reaction starts, how much product do you have? None. But now, guys, watch the way the dominoes fall. Because if you started with 0 and ended up with this, how much did it change? That much. This went up by 1.87 times 10 to the negative third. That one. It can't be. What's this number and that number?
Well, it's
Sure you do.
isn't it multiply like 1 times 10?
It's stoichiometry. So guys, think about this. So if you end up with 4 of these, how many of each of those did you lose? 2, right? Divide by 2. Does that make sense? So you will lose half as much of these as those you produce. So now we've got to take this 1.87 times 10 to the negative third and divide it by 2. And I get 9.4 times 10 to the negative 1, 2, 3, 4. So we get 9.4 times 10 to the negative fourth, but that's going down. And 9.4 times 10 to the negative fourth, and that's going down. Not yet. But now do you see what we can do? We can subtract. Because, guys, we started with 1 times 10 to the negative third, and we've now identified how much we lost. Subtracting the two will tell us how much remains. So we can go 1 times 10 to the negative third and subtract from that 9.4 times 10 to the negative fourth. And when we subtract, being horrible with significant digits, I get 6 times 10 to the negative 1, 2, 3, 4, 5. And doing the other subtraction, 2 times 10 to the negative third, again, minus 9.4 times 10 to the negative fourth, I get 1.06 times 10 to the negative 1, 2, 3. Look what we just came up with. All of the equilibrium conditions. Now we know the molarity of H2, the molarity of I2, and the molarity of HI. What do we do with those? Plug them into the Kc expression and solve for Kc. Do we need to do that? Does that just feel like algebra? Is it unsatisfying to not actually come up with the answer? Or are we okay? You okay? So guys, if you don't understand, we don't need it. So 1.87 times 10 to the negative third squared divided by 6 times 10 to the negative fifth times 1.06 times 10 to the negative third. Do the math, that gives you Kc. So guys, that's the power of this icebox structure. It allows you to pull together in an organized way initial conditions if they're given, equilibrium conditions if they're given, but significantly, the other thing that it allows you to do is it allows you to do prediction, where it says, okay, if I end up with this much product, I know what my change is because, as Brandon very enthusiastically pointed out, this was 0, so this went up. And then it allows us to think about the stoichiometry that says if this goes up, these will go down by, in this case, half as much because it's a 2-to-1 ratio. And it allows you to do all of that thinking in a way that, guys, frankly, I don't remember how I approached these problems in college. But this is better. And this is how we do it. Go ahead.
If the ratio is different, change the amount. That's half the time.
Yeah, so what if it was this? Well, you would divide by 2 and multiply by 3. Is that okay? But frankly, you won't see things that complicated. So guys, do you understand the structure? Because this is about to get better. You okay? Okay. You ready for an ed psych term? Scaffolding. So guys, what we're going to do is we are going to progressively pull away support. The first problem I solve completely in front of you. So if you're thinking to yourself, okay, I understand this, I know how to do them. No, you don't. You know how to watch somebody do them. But you don't know how to do them. So what I'd like to do is this. Let's read together. It says a 1 liter flask is filled with 1 mole of H2, 2 moles of I2. Kc at 448 is 51. What are the concentrations at equilibrium? Guys, you'll notice that we're using the same equilibrium. Temperature is different, so the K value changed. But guys, same reaction because it's familiar. Here's what I want you to do. Set up your icebox. Go ahead. Did you like the fact that it's now 1 mole? Oh yeah, 1 divided, that even I can do. And I went to public schools. In Wyoming. You guys stuck?
No.
No.
No help, yeah.
I'm debating on whether I should let you get deep into this before I... All right, I respect that. It frightens me, but I respect it. The last thing we need is you guys thinking, because you're just going to get in trouble. If I were serious, that would be wildly demeaning. My only concern is I've only got one more sip of coffee left, so we better get done with this quick. It's gone. But guys, please understand this. All the further I want you to get into this is set up the icebox. Please don't get into the solving of this, because that is where I'd like to help. So can we talk icebox? Okay. So again, we've got H2, skip some space, I2, skip some space, 2HI. I'm just going to go ahead and do this because I know it's going to be necessary. And then, guys, I'm going to wait to write the KC expression because I know this is going to get big. So, it's already balanced. And, guys, remember how bad I was about significant digits on the previous problem? This is going to be worse. So, we know we need molarities. I chose a volume of 1 liter, and I know I said these were in the book. This one I changed a little bit. So, guys, a volume of 1 liter, conveniently 1 mole and 2 moles. We got whole numbers. Ready? So what do we know? Well, it says a flask is filled with 1 mole of this, 2 moles of this. There's Kc. What are the equilibrium concentrations for all 3 of these? So let's use the icebox to gather information. Do we know the initial molarity of the H2? Well, we know the initial moles. We can convert it to molarity. Moles is moles divide by 1. 1 molar. Is that okay? And again, guys, I'm going to be horrible with significant digits. It's not the point. Now, guys, what about the initial concentration of I2? Do we know it? 2 molar. All right, Brandon, do we know the initial concentration of HI?
Oh, yeah.
Oh, yeah. What is it?
0.
Yeah. The irony of when you miss that on the test is going to be wonderful. Yeah. All right. Now, guys, here's the sobering part. We don't know anything else. That's it. That's what we got. Now, we understand, and again, I don't want to write, well, I'll write it down. Please don't write this down, but I will. So, Kc, we understand, is going to be HI squared. Sorry, I'm being really sloppy. Well, sloppier. H2 and I2, right? So, guys, the end game here is we want to know all of these. We've been given Kc. So we need to solve for all these concentrations. So, guys, fundamentally what that means is we need to know this and this and this. So to get there, given our icebox structure, what do we need to know? Change, right? We need to know change. In the previous problem, we were able to deduce. We were able to deduce the change by saying if we start with none and end up with some, the change has got to be the sum. And if that's what's going up, the other two have got to be going down. But guys, we've got no clues. So what do you do mathematically when you don't know values? You replace them with variables. And so it goes like this. H2 is a reactant. What happens to reactants during reactions? They go away. How much? We don't know. Let's call it x. We don't know the value, but we do know is it's going down because it's a reactant. So if that's going down by x, what's going to happen to that? Also down by x. Nah, close. Yes. So guys, what's going to happen to this? Well, it's a product. So it won't go down, it'll go up. But by how much? 2x. Right? In the same way that when we knew this value, we divided by 2 to come up with this value. If we're defining this value as x, we're going to define that as 2x. Guys, notice that we were smart about this. Please don't write this down. But if we had defined this as x, what would those be? Half x.
Hey, doing Mr. Hamburger?
Awesome.
Can I get some plastic money?
Yeah, except for I really screwed up and Karen hates me. So, are you going to the store? Oh, good. Yeah. Well, because Brittany went to the store and then I lost the receipt. Yeah. I know. You don't need any help. Hey, so guys, let's reconnect there. Notice the problem. If we had defined this as x, those would be half x's. Does that make sense? But that makes the quadratic formula really hard to solve. Here we go. So now, guys, let's establish our equilibrium values. We start at 1, we go down by x. This will be 1 minus x. We start at 2 and go down by x. This is 2 minus x. We start at none and go up by 2x. That is 2x. Now, guys, here's what we're going to do. We are going to take these values and plug them in to this expression. You should have room on your paper to work down. I don't, so I'm going to have to switch between pages. And guys, yeah, I'll just go here. So we've got Kc is equal to, sorry, I sort of cramped up there. So Kc is equal to Hi, that guy's squared, right? Yeah. Okay, and then H2, and then I2, and then, guys, we know Kc, it's 51, and that is equal to our Hi, going back here, our value for Hi is 2x. So that means this would be 2x, the quantity squared. And then our H concentration, our H2 concentration, is 1 minus x. And then our I2 concentration is 2 minus x. And guys, we got to solve this for x. So what do? Well, let's do some math. So we've got 51 is equal to 4x squared. Is that okay? Now we need to work with our denominator. When I was in high school, we learned what we call the FOIL method. Do they still teach that? First, outside, inside, and last. So however you think about expanding these things, 1 times 2 is 2. Then negative x times 2 is negative 2x. 1 times negative x is negative x. So our center term would be negative 3x. Is that okay? And then x times x is plus x squared. Is that okay? We good? Okay, so now, guys, this is how I would solve this. I don't know what they would have taught you. But what I would do is this. We understand that to solve this, we've got to bring this up, right? And we could distribute the 51 through this entire thing. We can do something first, though. Divide both sides by 4. So when we divide this by 4, that goes away. 51 divided by 4 is functionally 12, let's call it 12.8. So now we've got this. I'm going to write this over here, is equal to 12.8 is equal to x squared, and then divided by 2 minus 3x plus x squared. Is that okay? Did the algebra gods smile on that process? Okay. Would you have done that? What would you have done? That's fair. So now, guys, we're now ready. And can I do this all at once? Functionally, what we're going to do is multiply this by that, right? Bring the denominator up. So 12.8 times 2 is 25.6. I'm going to go back down here. So 25.6 minus 38.4x plus 12.8x squared is equal to x squared. Am I okay? Is that all right? Now, guys, I'm going to go down one more line, and then I'm going to switch screens again. So how do we solve this then for x? Well, we've got to set it equal to 0. So we need to move over that x squared. So subtract x squared from both sides, and we end up with 11.8x squared. But then let's put it in standard form where we have decreasing powers of x. So we've got 11.8x squared minus 38.4x plus 25.6 is equal to 0. Now, how do we solve this for x? Quadratic formula. Or, if your calculator will solve this for you, that's fine. I know that these TI calculators, if you plug that equation into your calculator, will give you the solutions for x. But we can do it together. So guys, x is equal to negative b plus or minus the square root of, is it b squared minus 4ac all over 2a? Did I make that up? If you had my show, I think you know a song. What is it? But does it do this? I don't even know if this is right. I'm just doing that. Is that real good? Okay, so then guys, jumping back and forth. Negative b, where b is negative 38.4. So that would be 38.4 plus or minus the square root of negative 38.4 squared minus 4 times a, which is 11.8, times c, which is 25.6. And all of that divided by 2 times 11.8. So guys, continuing to work this down, we get 38.4 plus or minus. Let's do this math. So negative 38.4. Square that dude. Then 4 times 11.8 times 25.6. Subtract those. Then take the square root. And I get 16 point, being loose with significant digits 3, and all that divided by 23.6. Can anybody confirm or refute that? Am I okay? Oh, good. Okay, so then, guys, we get this. 38.4. Let's do the positive case. Plus 16.3 divided by 23.6. And I get 2.3, or 38.4 minus 16.3 divided by 23.6, 0.94. So, guys, wait a second. No, it's not. It can't be. Maybe the problem is we rounded. Oh, yes. No, it is right. I'm sorry. It is right. Never mind. We're right. So, guys, those are the two possible answers for X. Let's talk. Guys, think about this, because they both can't be right. Because, guys, think about what these numbers represent. I understand that in math class, you do calculations and they have no context or meaning whatsoever. You write this down on the test, your math teacher pats you on the back because you know how to do math. But guys, the problem is these numbers are no longer sterile. These numbers mean things. And these numbers are representative of something that's happening in a chemical reaction. And chemical reactions can't do two different things. They can do one or they can do the other. Math would say they have choices. The chemistry gods say no, they don't. So now we need to talk about these numbers in context. So guys, one is 2.3, one is 0.94. What do these numbers represent looking back at your ice boxes? Change. So now guys, let's go back. 2.3, 0.94. 2.3, 0.94. So guys, let's talk about it. These numbers represent change. How much reactant we're losing and product we're gaining. Consequently, one of these numbers, can I use the term with you, is nonsensical? Makes no sense. Which one? Why is the 2.3 impossible? You can't lose 2.3 molarity of a substance that you only started with one. You can't lose more than all of it. So guys, the 0.23 is the nonsensical answer. This is an important check. If you do this math, and again guys, you're welcome to, you don't have to show all that work on the AP test. They'll just let you hit this with your calculators. But if you do this math and both of your answers are plausible, you can be sure they're both wrong. Because when you do this problem-solving process, the quadratic formula always will result in two answers, and one of them has to be impossible. So it's a good error check. So it's 0.94. So guys, what do we do with that then? Well guys, this is the way they require you represent this on the AP test. Your last step then goes like this. Concentration H2 is equal to 1 minus X is equal to 1 minus 0.94 is equal to 0.06 molar. Concentration I2 is equal to 2 minus X is equal to 2 minus 0.94 is equal to 1.06 molar. Concentration HI is equal to 2 times X is equal to 2 times 0.94 is equal to 1.88, if I did that math right. Hey, I did. I can multiply by 2. But guys, that's what that final step looks like. You need to show the process of coming back to the bottom of your icebox and reinserting those numbers and coming up with answers. What do you think? You guys okay? Crazy funky stuff, right? By the way, just so you know, if some of you are sitting there going, so you're telling me we're going to be using the quadratic formula for the rest of the year? guys, what you're going to find out is that when we put these problems in the context of acid and base reactions, some magic things happen that make the quadratic formula unnecessary. We'll get there in the next unit. No, it's not calculators. It's actually really cool rounding issues. You'll see, it's neat. So, guys, questions on the process? You're good? Okay, so guys, here then is your homework.